name is Micah, and me and Cooper will be showing you how to perform the snapshot in hockey. The snapshot in hockey is an important tool for a player to learn in order for them to score goals for their team. The snapshot allows for a player to quickly shoot the puck off the ice and into the net with a high velocity in the short amount of time that they are given. NHL professionals such as Connor Bedard and Austin Matthews can perform this shot efficiently and effectively, allowing for them to be one of the biggest threats on the ice.
Korchinski for Chicago, sent it across.
Stankoven gets it to his forehand, pivot clean, and just a quick.
During a snapshot in hockey, the player uses a quick and controlled motion to transfer energy from the stick to the puck. The shooter flexes the stick to create elastic potential energy, as the stick straightens rapidly and transfers energy from the stick to the puck, sending it flying off. It is used when you need a quick shot to hopefully catch the goalie off guard.
How to take the snapshot. Now, when performing the snapshot, the player holds their stick with a top hand in a pronated grip, while they hold their bottom hand in a supinated grip. Once your grip is set up, you want to push the puck out in front of you to create separation between the stick blade and the puck. Now, since we're on ground, I won't have a puck, but I can still show you the movement of it just with my stick. First, you want to start out with your hands away from your body. As you pull the stick closer to your body, you want to make sure you keep this top hand out to then be able to push into the ground, creating a stick flex, and then dragging it to be able to create force into the ground, being able to transfer it into the puck to have a harder shot. So in order for you to transfer your weight from your inside leg to your outside leg, you want to keep your weight on one leg, but then step into your stance to then be able to have more flexion in the stick, creating a bigger force into the ground to then be able to shoot the puck. Right now, we're on the ground, but in the next segment, we'll be taking you to the ice to show you a better demonstration. Here we will observe how the player uses the work energy equation to launch the puck with speed and efficiency. When solving for the work produced in the shot, we can simply multiply the force by the cosine of the angle and then by the change in distance that the puck experiences. As we slow down the shooter's motion, we can notice how the player slightly pulls the puck back in a stance, which represents the change in distance. Next, we can see how he puts force into the ground with his stick, causing it to flex and be shot in the air at a certain angle, which represents the cosine of theta in the equation. Lastly, we can observe how elastic potential energy is converted into kinetic energy through the connection between the stick blade and the puck. The formula for elastic potential energy is 1/2 kx squared. The spring constant in this situation is the flexion of the stick, while x is the change in distance of the puck. Through this system of elastic potential energy, most of its energy is mainly converted into kinetic energy into the puck, allowing it to fly at a higher velocity.
Before we go over what happens to the puck, let's start with where most of the energy comes from, the stick. When buying a hockey stick, you'll notice a small number on the side that mentions the flex. The flex of a stick is how much force is required to flex the stick 1 inch. The higher the flex, the stiffer the stick is. For example, a 100 flex stick takes about 100 pounds to bend it 1 inch. This is relevant because this is where most of the power in your shot comes from. The equation for elastic energy is 1/2 kx squared. In this case, the stick's flex is the spring constant. Since a stiffer stick means a higher spring constant, it means that it will usually produce harder shots, though there is a point where a stick will become too stiff where a person cannot bend it enough to create enough energy.
Position and velocity versus time graphs. First, we will take a look at the position versus time graph.
Looking at the graph, we can see that the x position of the graph increases linearly with a constant rate, while the y position of the graph is decreasing at an exponential rate. The reason the x value increases linearly at a constant rate is because the puck is constantly moving to its target in the positive x direction, producing a very tiny amount of drag in a short period of time, causing the idea of the puck moving back in its negative direction to be negligible. On the other hand, the y position exponentially decreases due to Newton's third law, which is, for every action there is an equal and opposite reaction, therefore causing the puck to decrease once it reaches its peak and fall down due to the force of gravity. For the velocity versus time graph, we can see that again, the y velocity decreases exponentially, while the x velocity constantly increases at a linear rate. The velocity of the y component decreases again, due to Newton's third law of motion. Since gravity is decelerating the puck mid-flight, the puck experiences downward force of negative 9.81 newtons, aka the force of gravity. On the other hand, throughout the puck's entire trajectory, its x velocity will remain the same until it hits the back of the net, causing it to then be stopped.
As the puck flies through the air, it is constantly losing energy. The puck's initial kinetic energy slowly gets turned into potential energy as it goes up higher in the air. This means its velocity slows down. This continues until the puck reaches the top of its arc, at which point all the puck's kinetic energy has turned into potential energy. When the puck starts to fall again, its potential energy will turn back into kinetic energy as it speeds towards the ground. The puck is also constantly losing energy due to drag or air resistance. This is due to the puck having to push through the air molecules, which are pushing back against the puck in the opposite direction, causing it to slow down. As you see in the picture, the Magnus effect is acting on the puck, but we won't get into this because there's little to effect on the puck. So it is there technically, but it does not affect the trajectory to which a point where it makes any kind of difference. Considering the equation work equals force times distance times the cosine of theta, we see that the amount of work done is influenced by the angle, the force, and the distance. This shot is one of the more difficult shots in hockey because of the small time or distance the player makes contact with the puck. This means that the player is not applying a force over a long distance, making force a more important factor. In a wrist shot, a long sweeping motion is used to apply more work to the puck. This uses more distance, so less force is required to get the same amount of work. But the issue with that is it shows the goalie that you're going to shoot, giving them time to react. The snapshot advantage is a short snap done by the stick to transfer a lot of force into the puck over a short distance. It takes time to learn how to apply force in a short distance, but if done correctly, it is worth the effort.
Yo, check it. We talking about momentum in the game, physics in the mix, it's never the same. Velocity and mass, they play in their part. In this cosmic dance, it's a work of art. Newton's laws dropping like beats in the street. First law of inertia can't be beat. An object in motion stays that way unless a force acts, trying to make its way. Momentum physics is the rhythm of life. In this grand equation, we navigate this drive. From the push to the pull, the forces in play. We ride the waves, no time to delay. Second law, F equals ma. Force and acceleration, no time to play. Multiply them together to get that push. Feel the momentum and that rush. Third law, action and reaction. For every action, there's a satisfaction. In this rap game, it's a chain reaction. Like dominoes falling, no need for subtraction. Momentum physics is the rhythm of life. In this grand equation, we navigate this drive. From the push to the pull, the forces in play. We ride the waves, no time to delay. In the universe's symphony, we find the beat. Gravity pulling like a heavy feet. Angular momentum, we spin around. In this cosmic cipher, we're gravity bound. So here we are, in this physics groove. Momentum in the rap, it's the way we move. From the atoms to the galaxies, we're all connected. In this cosmic dance, we stay respected. Thank you. Peace out.